Hello, today we are going to discuss the Melde experiment. It is a third semester experiment, and it is basically the aim of this experiment is to determine the frequency of an electrically maintained tuning fork. Now, you may ask, what is the need of this experiment? Apparently, nothing. But it's an important principle that we need to hold on to. It's basically one of nature's laws. Frequency of vibration of a thin metal sheet in different modes and vibrating lengths are related by Mohn constants. They are calculated by using the frequency and the corresponding lengths of the vibration strip. So, as we know that there is everything in this world has a natural frequency of its own, and when that natural frequency gets matched, it's called resonant frequency of the other object, which affects it. Now, what we are going to do is that we are going to show a lovely apparatus. We have got a thread. Well, in the book it's mentioned a metallic strip, but apparently we have a thread. And then on the other hand, we have a metal fork dish hanging on the other side to support some weight. This is a very strong stand that has been used to keep that in place. And this is the main apparatus that we will talk about. This is an 8-volt battery voltage that we will supply, and this is the electrically maintained tuning fork. So this entire thing is a giant tuning fork apparatus. And this is the stand that has been held itself into, and these are connected to the AC battery from which we will be conducting our experiment. The first mode that we want to talk about is the longitudinal mode. The longitudinal, as from the name itself, it refers to being perpendicular. So the currently the vibration, the propagation of the vibration, the propagation of the frequency waves are perpendicular to the direction of where the string is leading to. So when we see here that we will first of all we will connect this AC battery, keep it to a like a minimal voltage of 6 volts. Turn it on. Then we're going to turn our attention to this screw. So be very careful when I talk about the screw. Is that I want to show you something. You can see the gap between the screw. Okay, and I'm going to adjust it as per to create a frequency. As you can see, you can hear a light sound until the air gap is perfect for a natural frequency to occur between the oscillating tuning fork and the current that we're supplying. It's an AC current. So you can see if I move too far, I lose it. If I move too close, I completely kill the gap. But if I come somewhere in between, you start to have a resonating frequency that is that you can stabilize, and that gives you this. Well, currently it's an unstable mode, but you can see how beautifully things are moving. And also, don't let go of the screw while doing this, because when the fork is vibrating, it also vibrates the screw out of its original place. So when we'll be doing it in groups, you keep someone along with you while performing this experiment. So you can see, slowly stabilizing. I kill the gap again. As you can see, the number of modes here: one, two, three, four, five, six, seven. We've got 7 modes longitudinal. So you have to constantly keep them in stabilization by not letting go of the screw in the first place, because the vibrations of the entire tube forward will affect the screw and move it in directions. The Lenz's law, by the way. When we keep this in transverse mode, we get like almost, not almost, exactly the double amount of nodes that we got in transverse to the longitudinal. You see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes will be there in transverse, while in longitudinal, with that mass of 50,000, it was wide. You can see that there are two different tabular columns. One is longitudinal mode, one is transverse mode. So we just saw the longitudinal mode happen. So when we talk about this, we talk about this atomic weights that we have is the load that we're going to talk about. So they have got 100 grams, you have got 200 grams here. So apparently this is very fun set and it looks very beautiful also. So you find this atomic weight, you keep this on your side, and then we're going to proceed with something called as a tension. A tension, which obviously is mass into acceleration of gravity. Then what we're going to do is that we are going to measure the entire length of the vibrating string. Now, the length of the vibrating string will extend from that tuning fork till the point here it touches the pulley, okay, not beyond that. So, and also as we can see, as you can see, we were counting the number of segments that were the nodes, the vibrating nodes, positive nodes. You have to count them, you have to mention them here, and then according to it, we will divide it by segment length. It was each point of the since each point of the string was vibrating, we will divide it equivalently, divide by 7 and the length of the string that we have. So you will get this segment length. And then when we divide the tension with the segment length, because each tension will give us a different length. So this should come to be almost constant. And the same principle goes for the transverse mode.